Welcome to the ET380 lecture video for digital modulation. Here I've showed a basic chart for digital modulation, and this varies quite a bit among engineers. But anyway, amplitude modulation, where we modify the amplitude of the signal, and we have OOK, on, off, and asks, AM shift key, and QAM. Frequency modulation, where we change the frequency, and we have FSK through QFSK. Phase modulation is where we change the phase of the signal, and here's our list of the ones that we're going to cover. Besides these, we also have amplitude phase shift keying, where we combine ASK and PSK, and also quadrature amplitude modulation, and we'll get into that too. Okay, if we break out amplitude modulations, we have the OOK and ASK and quadrature, which I'll cover at the very end. Okay, here's a little block diagram of our OOK modulation. So we have a digital signal in, we have a carrier signal into a modulator, and what happens is this turns on and off, and it passes the carrier signal. So this is mainly used for Morse code or on other on-off type signals. Here we have amplitude shift keying, ASK. We input digital information through a modulator, and we have two carrier signals input. So if it's a 1, it'll be the larger carrier, and if it's a 0, it'll be the lower amplitude signal. So we can tell the difference between zeros and ones. Here we have a 4-level ASK, where we have 4 different amplitude carriers entered into our modulator. And if we have a 1, 0, we get this amplitude. If we have 0, 1, we get this amplitude. If it's 0, 0, we get this amplitude. And if it's 1, 1, we get this amplitude. Okay, let's look at frequency modulation. So FSK, we have basically FS frequency shift keying, or binary frequency shift keying, or they just count the bits. Minimum shift keying, which I won't cover. MFSK, multiple frequency shift keying, or M-area orthogonal modulation, or QFSK. Here's a little bit of frequency shift keying. So we have 2 oscillators, and we combine them into here, and we put in digital information, which is this switch. So we switch back and forth between these 2 frequencies. So we have the higher frequency here representing 1 digit, and the larger one of another digit. So those will be 0s and 1 based on the frequency. Okay, here we're looking at frequency shift keying as a waveform. So we have 1s and 0s. So 1 would be the higher frequency and 0s would be the lower frequency, and we can tell the difference. Okay, we have MFSK, which is multiple frequency shift keying, and I'm showing 3 frequencies, but they could be any amount of different frequencies. And we select between the 3, and that will be representative of binary information. Okay, let's look at phase modulation, where we're changing the phase of the signal. So we got PSK, phase shift keying, BPSK, which is binary phase shift, differential phase shift, and quadrature phase shift. Okay, let's look at binary phase shift. So what we're looking at here is the digital signal either going high, 0 to 1, or going low, 1 to 0. Okay, rising edge or falling edge. And if you look at it, the rising edge is represented about this signal here, which is the top one. On the falling edge, we look at this waveform here. So this binary phase shifting only shows this signal when there's a change, either going high or going low. And anytime there is no change, it just will be the carrier signal. Okay, DPSK, differential phase shifting, is we're looking for a phase shift. When we get a phase shift, we're going to go to 1. So wherever there's a phase shift, we are going to output a 1. So if we have no phase change, it stays at 0. Okay, QPSK, quadrature phase shifting, we're looking at representing different binary pairs, 0, 0, 1, 0, 1, 1, 0, and 1, 1. So that's 0 to 3 decimal. And when we have this phase, we're going to, at 45-degree phase shift, we get 0, 0. At 135, we get 0, 1. 225, we get 1, 0. And at 315 degrees, so we have to match these patterns with these different binary pairs. And we'll get a little deeper into this. Okay, let's look at quadrature. And this applies to both, actually all 3 types of signals. So what we have here in red is a sine wave, because it crosses at 0 and 180 at 0. So a cosine wave is 90 degrees offset, phase shifted. So the green one would be a cosine wave. Here we have our sine and our cosine wave, and wave theory says that if you're combined, they add, or if they're on the minus side, they subtract. So when you combine 2 waves like this, we result in a larger wave. So what we're doing here is we're summing the cosine and the sine waves, and this thick light blue line is the resultant wave. Okay, so what we've done here is we inverted the cosine wave. Sine wave remains same, and we invert this, and we end up with this waveform combination, but it's at 135 degrees. So this allows us to make a different angle that we have. So where this one is at 135, we essentially have 0, 45, 90, 135, 180, 225, and 270. So we have more angles that we could use based on these sine and cosine. Here I'm showing QPSK, quadrature phase shift keying. This diagram's also the same for QAM, quadrature amplitude modulation. And what we've done is we've plotted Q, which is a sine wave, and I, which is a cosine wave. And we have plotted 4 in our quadrant. So this is quad. We represent 2 digits, binary digits, 0, 0, 0, 1, 1, 0, and 1, 1. And these are offset at that angle. So this one represents IEEE 802.11, which is Wi-Fi, and it's also called 4QAM. It also matches that. Here I'm showing a 16-point quadrature map, and this is 16 QAM, quadrature amplified modulation, but it's the same for the PSK. And what we've done is we've mapped out these are our first 4. If we had 8, they'd be in between, but this is 16. So at 45, we have 1, 1, 1. And way out over here, we're going to have 1, 0, 1, 0. So what we're able to do is get a 4-bit number which is going to go from 0 to 15 decimal. And using these out of phase signals, we can go ahead and produce a 4-digit binary number. Okay, here's a map going from 4, 16, 32, and 64 points for different QAM signals. They actually have 256 and 4096, I believe now, for 7. So anyway, okay, here's a Quadrature 16 QAM vector analysis. This is used at a vector scope, and this is what is necessary for these Quadrature signals. So we have a dot that represents our 16 points. The little circle around there is our error limit. Okay, and that's programmed in. And here's our vector diagram showing the different paths of all these signals as they test it. And this one is very good because everything is within the circle. Anything out of that circle will be bad, but this is a good plot.